Yeah, so this is probably the first exploration conference or symposium I've ever been at where there's been more than one talk, and in fact we've got 4 talks today where we're talking about oriented core and structural data. So thank you to the organizers. We can make 2019 the year of structural data. So please excuse me if I repeat some of the stuff that's been said in some of the previous talks, as there is a little bit of overlap, but I'll just try and drive the point home a little more. So thanks very much also to Jamie from the CSA Perth office, who helped me a bit with this talk. And I'm going to try and put a presentation to you guys about not how to measure structures in core. There's lots of online resources on that, but how to think about designing a structural drilling program and to make sure that you set out from the start to get the information that you need at the end. And I will spend a little bit of time, we've already heard about it, on some of the QA/QC stuff that you can do. We spend a huge amount of time in exploration doing QA/QC on geochemical data, on things like downhole data, in terms of drill core orientations, or drill hole orientations, sorry. But there's almost no attention given to quality control on structural data. And it may be one of the reasons why it very often doesn't get used, is because people just don't really have confidence in it. So if you set out from the beginning with the aim of collecting quality data, then perhaps more people will start using oriented core data. So when we're setting out to do a structural drilling program, we first want to sort of decide what we need. Why are we collecting this data in the first place? And then we're going to design a drill program with that in mind to maximize the value that we can get from that drilling program. We need to then spend the time to make sure that we get quality-oriented drill core, make sure that we're collecting structural data appropriately, and that there's some quality control checks on that structural data actual collection. And then we can use the data in whatever analysis we want to do to get back to the original question that we had in mind. And so the first step is deciding why we need to collect this data, and then with that in mind, designing a drill program. So why would we go out and acquire structural data? Obviously, if we've got structurally controlled mineralized systems, we want to understand the controls on on that mineralization. We want to understand the orientation, and we want to use that, hopefully, to target more mineralization. Very often, these days, especially as we're doing more and more exploration undercover, we don't have nice outcrops like this to work from, and often the only place we can get any structural information is from our drill core, and so we really need to focus on getting the best data. We also want to use that data to create 3D models or structural models. We've seen a pretty nice one in the previous talk, which shows what you can do when you've got quality structural data. It's very useful when interpreting geophysics to have some structural data to work from. And probably the most commonly used scenario is geotech modeling. So I guess in my experience, most of the structural work that I've seen has been focused around collecting structural data for geotech modeling, so you don't end up with situations like this. And in each of these cases, we will design a program differently depending on what we're trying to get out. So if you're trying to understand mineralized systems, you would be trying to orient your drill core perpendicular to those mineralized systems. If you're designing a program to get geotech information, you want to be designing your drill holes perpendicular to those structures. So setting out with some idea in mind of what you're looking for and making sure you design your program appropriately will help you to get the data that you're looking for. And here's just a quick example of, you can't really see these holes super well here, but what you can see is that there's a main trend of mineralization, and by and large it appears that the drill holes are going in perpendicular to that mineralization. So you might say, well, this was pretty well done, and they generally went across the structural trend, but you can start to see, if you look closely in this example, that there's something which looks a bit funny going on over there. Mineralization seems to be fairly suddenly terminated at that point, and there's no drill holes going through. So that might be an instance where we would look at putting a drill hole in a different orientation to try and figure out what's going on there. So spending the time beforehand to examine the existing data and to plan your drill holes carefully is really the first step in getting quality structural data from a drilling program. Once we've got that and we've designed our program, we want to make sure we have properly oriented drill core. And this is probably the most critical step in the whole process. If you don't have quality oriented drill core, you can't collect proper structural data from it. Or you can try, but the data might be meaningless at the end of the day. So this QC of oriented drill core is really where you should pay attention. And it's not like assays where you can go back and do some checks, re-assay things, take more samples, resubmit them to the lab. This QC needs to be done when the drilling is being done on site, and any errors need to be picked up immediately, or you kind of start wasting your whole exercise. So how do we improve data quality in structural logging? And so the first step, once we've got an appropriate program, is to make sure you've got correct core orientation and markup. Those two go together. Knowing the structures and understanding the structures, measuring them correctly, logging those structures in sufficient detail so that we can get queryable data sets out of it, and making sure that we do logging QA/QC in addition to getting QA/QC on our core orientation. I'll try and go through a little bit about each of these steps. So first of all, core orientation. There's a whole bunch of different orientation tools out there. Hopefully most people are using one of the modern things like a DeviCore or a Reflex ACT. These tools use accelerometers and time stamping technology to orient your drill core at the time of the core break, so that when you pull your barrel out, you know the exact orientation of that piece of drill core as it comes out. The old technologies, which were using these kind of pencil markers or a spear, which you threw down the hole and kind of hoped that it would bump in the right place, prone to large errors. You can see here a spear mark which is pretty close to the center of the core. Lots of uncertainty when you see something like that. Or you can get these big smears in your pencil marks, giving you huge error on those core orientation measurements. So these modern tools are much better, but you still need to make sure you've got a good crew who understands how to use the instrument and knows what they're doing. And you also need to have a geologist on site, on the rig, making sure that your orientation is done correctly as that drill core comes out of the hole. And second to that, as the drill comes out, as the core comes out the drill hole, you want to make sure that you are marking up that core as soon as possible. And when that core is being marked up, you need to make sure that it's reassembled properly. This enables the geologist to check that the drillers are orienting the core correctly, and so you can pick up any errors in real time and correct the problem. So you don't land up drilling whole boreholes with poor orientation data and start wasting that structural opportunity. And you can start picking up things like these lock offsets, where you can start picking up slight differences in core orientation between runs and start giving confidence gradings to your core orientation. And I'll get to a little bit more about that. We've also heard a bit about that earlier. Now, for I think a lot of people is the most confusing part of the whole thing is what structures to measure. And there are a huge range of structures. We've got here, for example, a foliation and a little vein. And depending on the orientation of that core, they could be at exactly the same depth. And so you need to make sure that you're logging all the structures that you can and make sure that you're logging the appropriate structures. So very often people will log joints or veins because they're the easiest things to identify. But there's a whole bunch of other stuff that you can be looking for. So, for example, here we have faults with a fault breccia, veins I've already spoken about, shears, which come with their own complications. Here you're actually looking at a shear, and you can actually see shear sense indicators within that shear zone. And you want to pick up that information on shear sense as well as just the general orientation of the shear zone. Folds, which can have a particular vergence and can be an indication of a larger scale fold structure. And the big neglected one in structural geology I often find, lineations can give you so much information, but they very often just get completely ignored. I mean, here's a nice example where you can see a lineation, and that will often give you very good information about movement directions on faults, but if that information isn't recorded, then you've lost out on an opportunity. The other thing to consider is how many measurements to take. You want to log in detail, but you can also, if you've got a structure that's repeating consistently through your whole drill core, you want to probably be logging that every meter or so. And then you want to start logging all the characteristics of each structure that you're measuring. Things like how thick is the structure? What is the mineralogy of that structure? Is there a particular texture? Are there cross-cutting relationships? What's the color of that structure? Number of streamular structures per meter? And to start building up a database that once you have this and all these structural measurements, you can start querying that data and creating subsets of that data to really start analyzing your structures. And this is so that you don't avoid this, what I call the structural data conundrum. So in structural geology, you want to have lots of data. Geological structures are inherently variable, and so you really want to try and get big data sets so that you can do some statistical work on them. But if you don't collect data appropriately, you'll end up with a situation like this. Here's an example data set where they just had structure type is vein with no other information, and it's essentially meaningless. So what often happens then is you start getting less data, but at least some of it might be quality data. But ideally, we want to get to a point where we can collect lots and lots of quality structural data. And so when you're setting up your structural logging procedure, here's an example from Jamie. You've got all the different structures that you can select from your drop-down list. You've got things like fold vergence or shear sense, and logging that requires that the geologist who's doing the logging has a pretty clear understanding of the structural picture of what they're logging. So don't give it to your most junior geologist to go and log your structures. Relative timing is another important point to try and note. Very critical, mineral codes. What minerals are associated with each structure type? You can have alteration codes. You can have color. we can add a whole bunch here. And what we're trying to get to is observation and not interpretation. I've often seen when structure is logged, very often in the comments section of a drill log, people will say, this is X shear, and it indicates Y. So we want to get away from that interpretation in our logging into a purely observational sort of frame. And setting up systematic logging procedures for structural logging is part of that. And then finally, giving a confidence index to your orientation line. So this is done hopefully in a quantitative manner based on lock angles between different runs, but you can set it up in different methods for different scenarios. But you really just want to make sure that you've distinguished orientation data that you're confident in from unoriented or low confidence data. And when you're measuring your structures, there's lots of different ways to do this. The old school way of having a rocket launcher or and physically orienting your core in the same direction as it would be on surface. This is a useful analog tool, and it's nice to have one on site so that you can really start thinking about the 3D orientation of your structure. The one which a lot of people used up until now are these core protractors, which measure alpha and beta angles. They're pretty fast, and you can get a lot of data, but you run the risk of collecting a lot of meaningless data unless you convert those alpha beta angles back into dip strikes regularly while you're logging the core, and try and understand that data so you don't land up with a whole bunch of alpha beta angles which are incorrect or can't be related back to other observations. But fortunately, we've got some new technology. This IMDEX tool is really nifty, and it gives you real-time data that converts your alpha beta angles into dip strikes that you can view on a stereo net while you're logging, and enables you to do some QC during your logging process. And so to the sort of final point here is QA/QC of structural data is quite different from QA/QC of geochemical data. You have to make sure you get your core orientation done correctly at the rig. You cannot go back and fix poorly oriented drill core. What you can do if you do have poorly oriented drill core and you recognize it is you can start omitting it or filtering it from your data set. And then finally, when you're doing structural measurements, it's essential to have properly trained geologists on site who can recognize any unusual orientations and can query that. It's not something that's easy to do after the fact. So here's just the core orientation confidence again. You've got different models which you can come up with, but essentially a grading of level 1, level 2, level 3 for well-oriented, poorly oriented, unoriented, or for you can. I saw the guys earlier had 5 levels of confidence, and you can just see a little example here of a set of structures. That's the high confidence data. You can see a much tighter spread there. Level 2 data, level 3 data with a huge amount of scatter. It doesn't change the overall orientation too much, but it's important to note that you can, if you have got that core orientation confidence, you can actually start filtering this data and checking if you've got any effects from your orientation confidence. Making sure your geologist knows the core orientation, can orient the core by hand, can think about any marker structures. So if you've got a marker structure like cleavage or bedding that you expect to be regionally consistent and it changes suddenly, then you can start asking questions. You can go back and check, is there a problem with the core orientation, or is there really a big change in orientation here? And you can start flagging those issues as you're logging it. And then finally, there is a way of trying to filter some of the data using stereo nets after the fact, where, for example, if you've got a consistent structure type in the data set, you can start subsetting the data by drill hole, and then you can pick up things like most of that data clusters around single orientation, but you can see around scatter around here, which probably means we've got some core spin going on, and your structures are not properly oriented in that case. So, thinking about why we need the data, designing the drill program, QA/QC of the orientation, and collecting quality queryable data in a systematic database is the key to the whole thing. And hopefully, if we can get better at this process in the industry, we'll be able to start using our structural data interpretation and targeting much more in the future.